2 responses out of many more students. So when I have 4 responses, we'll review it. So just a couple more people submit, even if the answer is, I don't know. Okay, let's go ahead and dive in and review. Okay, so I wanted to make sure that everyone was on the same page about the concepts from the other night. There was some question as to whether or not they really hit home. Granted, you guys have had another evening to work on it, read some articles, but even though most of these answers are correct, I do want to spend a few minutes making sure that everyone is on the same page. So if you guys have questions, please unmute and let's have a chat about it, because this is actually pretty core. It's an important, so let's call it what it is. Recurrent neural networks and LSTM units in particular are the bread and butter of a lot of deep learning problems. So you need to be conversational about it. It doesn't necessarily mean that you have to memorize the math, as quite the contrary, actually. It's not necessarily intuitive the way a lot of this works. Okay, so what are recurrent neural networks? What are examples of what they do? So what I was looking for here was a talk. Oh, I like this one. Whoever just sent that in, nice job. Looping through hidden layers. So RNNs work through recursion, right? That's where the recurrent term comes from. And so what types of problems do they apply to? Well, generally it's sequential data, which can be time series data. It could be things like speech recognition, hand recognition, text recognition. Things like recurrent neural networks inform products like Siri and other spoken language-based inputs and outputs. I was about to say Cortana, but I don't think anyone ever actually used that. So let's think Siri and Hello Google. So it basically it's different from a traditional feed-forward network in that you've got that recursion step, right? Useful for time series, text prediction, speech recognition, and LSTM can be used to prevent exploding and vanishing gradients. Yep, let's talk more about that. So then my next question is, what are some drawbacks of recurrent neural networks, right? And how does the LSTM unit improve functionality of a standard RNN? So this one pretty much hits the nail on the head. They suffer from vanishing and exploding gradients. Now let's be clear, any feed-forward network can suffer from exploding or vanishing gradients. However, RNNs are more prone to it because of that recursion step and because you have so many more weights being updated. That exponential increase in complexity means you have an exponential number of gradients being updated, right? And so if you have, so that's in part why they suffer. But also because you have that recursive element, training's really, really hard. It takes a long time, right? It's computationally very, very expensive. So let's see, vanishing, exploding gradients are some of the biggest problems. Yep, overweighting most recent inputs. Yep, and this is another one. So bias towards more recent values. So they're not very good at remembering long-term, which is where LSTM comes in, right? So LSTMs have an explicit function in there that either allows for something to be forgotten. If it's either a 1 or a 0, it's that forget gate that I mentioned, but didn't go into a lot of detail on. And so if that forget gate is 1, it basically just allows the signal to propagate through. If it's 0,
that particular value is dead. And so that information coming through the forget gate, if that value is 0, it doesn't go anywhere, right? Yeah, so, okay, that was kind of the main thing that I wanted to address. And then talking more about the vanishing gradient problem specifically, or the exploding gradient problem on the other side. What is more likely to occur and what's a potential solution? So there are multiple solutions to it. I didn't review all of them, but this is where Google could be really helpful, or you could look at other articles. Okay, so the vanishing gradient problem occurs when the gradients are really small. The RNN doesn't update the weight. So if they're effectively 0, your neural network can just fail to converge, right? They no longer have an impact on training, which can lead to all kinds of problems. Extremely small gradients, right? Causing slow convergence or failure to converge, right? Yep, that's a great technical answer. Updating the weight through many iterations causes them to vanish. Yep, and so potential solutions, a potential solution includes changing your activation function, right? And so if one particular activation function is causing a problem, try a different one, see how that works. And this is a great answer. You're more likely to see, and to the second part of the question, when are you likely to see it? You can see it in any feed-forward network. However, it's more common when you have really, really deep, lots and lots of layers, right? And that's why RNNs are prone to them. More likely to occur with certain sigmoid functions, particular solutions, gradient clipping. Yeah, gradient clipping is basically where you, well, faster hardware. Yeah, but gradient clipping is where it will basically look at the gradient and prematurely stop the updates after it reaches a particular point. You know, so if it never gets to 0 or effectively 0, then gradient clipping will, you know, help. Yep, and some of these other batch normalizations. I actually need to remind myself how that is a solution. Sounds familiar, but I believe that is a solution. And just generally, yeah. Okay, great answers, guys. I do have my tune monitor set up going again, fortunately. So if you guys have any questions, feel free to leave them in the Slack. Otherwise, let's go ahead and dive into tonight's seminar. So tonight, we're going to talk about convolutional neural networks. Now, that is quite a mouthful. Go ahead and share this, share my screen. So this is pulled right from the, let's see, is this the correct? Yep, here we go. So this is pulled right from our GitHub, so you guys can download the repo directly into either SageMaker if that's what you want to use. It's not as necessary tonight. We only have one kind of long training thing that we're going to do. For other, you could almost run it locally, actually, but SageMaker is still our tool of choice for these more beastly networks. Okay, so let's talk about convolutional neural networks. So a convolutional neural network is one that convolutes over some inputs. Well, the best way to describe a convolutional neural network is one that applies to computer vision. And so applications of these are really generally on, are in things like image recognition, image classification, but you don't have to take my word for it. Let's go ahead and take a look at an example. This is embedded in your notebook. I'm going to mute it because I don't know how Zoom is going to play well with this. But basically, image object detection in video is an application. Facial recognition, Facebook's doing it.
it's actually kind of scary. I saw an article, I think it was a year ago, that someone had, with like 95% accuracy, developed an algorithm that allowed people to detect whether or not someone was gay based on their facial features, which is incredibly alarming from an ethical standpoint, as you can think, because there are certain countries that are not as LGBTQ friendly as the United States is. Not that the United States is great about it, but so yeah, when you start talking about personal identification, you really need to consider what it's being applied to. Anyway, so when you're talking about a person, that's actually a fairly straightforward task. But you have to think about what's kind of cool about this example is that we're not talking about hot dog or not hot dog. What we're talking about is effectively 3 dimensions, where we have a height, we have a length, and then we have something changing over time, right? And technically, color adds another degree, another dimension that we're not even considering here because we just think about it. But it actually does add another layer of complexity that we need to consider when we're building our models. So anyway, I mean, it's cool. It's had a lot of attention. And one thing that's really important to recognize is that this is also where GPUs have had a real advantage over traditional CPUs. We had a conversation during office hours a couple of weeks ago about what's the difference between a GPU and CPU and why do we care? Well, the popularity of these image recognition tasks has really brought GPUs to the forefront in these conversations. And actually, Dakota will share a link later demonstrating on the same problem how fast it was solved on a CPU versus an equivalent GPU. Really interesting stuff. You can also use really anything that involves image classification. So in my own field, in biomedical science, I was actually offered a job at this company once when I was first out of my grad program. And they were trying to do image classification based on radiology prints and basically trying to diagnose if someone had cancer or not. And it's another example where they've made a lot of advances, but there's so much nuance to reading those but more importantly, it's actually very, very difficult to get labeled data sets. So if you can imagine, if you want to classify hot dog or not hot dog, you just need a camera and someone to sit there and say, hot dog, not hot dog, hot dog, not hot dog, right? We all have an intuitive sense of what a hot dog looks like if you were born in this country, right? However, if I were to, ask Tina, hey, Tina, can you look at this image and tell me if this guy has cancer or not? No, and it's actually a very expensive exercise to label all those because you have to pay a radiologist to actually correctly identify those. And then you have to, since you're talking about something clinical, you have to do it twice to make sure that they agree. And if they don't agree, then you have to come up with some way to resolve the disagreement about what you're talking about. So there are a lot of challenges to dealing with in handling these image recognition problems, both computationally and in generating the data itself. And so consequently, you're not actually going to see a lot of these in practice except for very specific applications. They've done some very cool stuff, but I'd be lying to you if I said that most data scientists dive into convolutional neural networks on a daily basis. And so that said, our goal for tonight is to introduce you to the concepts, as we did with the recurrent neural networks, as we introduced you to the concept of long short-term memory. I want you to be conversational about it. I want you to be able to talk to an interviewer about it. And I want you to be able to get your code to run. My goal is not to have you have highly performant models, right? Because it takes so long to run these things. So 2 things. Focus on getting your code to run. Okay, don't focus too much on hyperparameter tuning on these. I mean, we want you to play a little bit, but as you guys have both said in your quiz answers and probably come to realize, they're very difficult to train. And so that said, what we're going to do is we're actually going to focus on a couple of toy data sets tonight. And so these are pretty well, there's lots of blog articles that will review the same topics that we're going to review tonight. So, you know, we're not curing cancer tonight or even diagnosing who has cancer and who doesn't. But it's still a really, really cool, I mean, I don't have to tell you guys, right? Like this is pretty awesome stuff. So let's go ahead and dive in. Okay. And I did want to take a moment to sort of jump back to, remember that first example that I talked about how neural networks work and how the eye works. Even if you guys didn't understand what I was talking about, that's okay. The concept that I was alluding to was you have these, you have certain neurons that respond to color. You have other neurons that respond to contrast, right? And you have certain neurons that respond to other things. And so what you do is you actually get a convergence. Those will send information to the next layer, and they'll send information to the next layer. And then I gave an example of something called the mirror neuron. And the mirror neuron is where, you know, within a couple of days of being born, a baby, if you smile at a baby will smile back at you, right? And the baby's a very complicated neural network, I'll give it that. But, you know, babies are not, you know, they're not making, you know, they're not going to be able to like offer you any kind of commentary on impressionist art, right? And that's in part because, well, they can only see so far in front of them when they're that young. But what they do is they've got these neurons that are firing, and so it's the pattern recognition, it's that convergence of bringing all that information together and translating it into something simpler, which is like, oh, you're smiling at me, I'm gonna smile back at you, right? And so they have to recognize that it's a smile, and then have their body respond in such a way that the adorable little muscles on their face are like smiling back at you, right? And so convoluted neural networks are a little closer to the biology than some of the other examples we've talked about. So it makes sense that, yeah, anyway, I'm going to get off my biology tangent there, but it's worth mentioning that these are a little closer to the actual understanding of the way the brain works than some of the other things we've talked about. Although LSTMs are not, they're actually pretty consistent as well, but I'm going to save that rant for office hours. If you guys want, just ask me about it. Yep. Okay. Okay, and if you want to know more about how, you guys can do some reading, or if you're interested, just send me a message and I'll send some articles. It's a little bit beyond the scope of what we need to talk about, and I'm a nerd, so I need to keep that part in check. But really cool how this sort of came together, and how we're now applying it. You know, from research in the 1970s all the way through to our current, application and image recognition. Okay, so let's go ahead and dive into the code, but I am going to check in on the channel. Oh, Annika, I really appreciate that comment about the sexuality detector. Yeah, I'm really glad it wasn't reproducible, actually, but even still, the fact that it even exists is scary, right? Yeah. And Annika also commented about self-driving cars. Oh yeah, actually self-driving cars are an incredibly important application. One of the scariest things about some of these image recognition studies is that early on, they actually had things like cat, dog, bird, right? And they were actually really, really, really good. for very specific tasks. However, and I have one more sample I want to talk about, or study I want to talk about, but as soon as you like turn the angle of the camera a little bit, even if you're photographing the same bird, it becomes an entirely different task, right? And so it really so a lot of these are not necessarily robust in 3 dimensions. And the other thing I would say is that there was one study that I read about, and actually, if you guys have a chance, read, there's a great book that came out, I think 2 years ago, called Weapons of Math Destruction. So I'm totally stealing this example from that book. It's an easy read. I read it over Christmas 2 years ago. It was very disturbing, but it talks a lot about the ethics of data, of machine learning products, and how they influence our daily lives and how they're kind of ruining some people's lives. So really good read for any data science student. But one of the studies they talked about was how they were looking at tanks and how they were trying to make predictions about the movement of these tanks, right? Or something like that. And at the end of the day, it had like 100% accuracy or something ridiculous like that. But the interesting thing was, it was actually only, the tanks would always move at sunrise. And then, move back at another particular time of day. But it was only predicting sunrise. It wasn't actually predicting the movement of the tanks themselves. And so just keep in mind what you're, in terms of experimental design in general, not just for image recognition, consider throw negative values in there. Make sure you have a variety of negative things. I mean, you don't have to go any farther than reading about, I think it was the Windows or something like that. One of the early, I can't even remember the technology, but they got a lot of flack for identifying Black individuals as monkeys. I mean, like, come on. It's just mind-boggling. And it was just because they didn't have Black people in their training sets. Like, make sure you have diversity in your training set and make sure it's representative of your population. Okay, so let's get into the code, because I want to make sure we don't go over tonight. But anyway, so really interesting, really kind of lots of important applications, but there's a lot of nuance to these particular types of problems. Okay, so we're going to actually dive in, and we're going to study a picture of Austin, our beloved CEO, right? What we have is we're going to import a couple of things. These are pretty familiar to you. We're going to pull the raw data from the image into an object we're going to call Austin. To make this a slightly simpler example, we're going to rescale it in grayscale. So grayscale has a lot of depth on its own, but for sake of time, we're not going to talk about color, although it's something that you do want to consider in your actual problems. And what we're doing is we're taking this and we're flattening it into an array, our huge matrix, I should say, that represents all the different values in this image. Because we can't, you have to vectorize it in order to have it play nicely with your model. So we're pulling it in, we're reading the file, we're rescaling it as grayscale, and then if we were decoding it, if we re-encode it as an image, we can actually see that it's just a grayscale image of Austin. So what is actually in this object? We have Austin grayscale.shape. This basically means that it's a 400 by 400 image, where each element in here represents a single pixel. Okay. I want to pause for a second. Gwen, I don't actually know what that means. If you could leave a little bit more information.
I got that error when I tried to run that first cell. It seems to be something NumPy is trying to import when that first cell runs. And I'm connected to the same kernel as you. Yep, there it is.
Okay, I'm having an issue too. Okay, hold on. Let's go ahead and, that's interesting. I'm running just fine on my other one. Image.io, psychic image. Okay, I'm gonna try to copy this over. Image.io, PLT. Oh, that's interesting. It's running just fine on my other instance. Okay. That is weird. Is there something that I didn't run? Hold on. Oh, that is very strange. Let me get back to that. Ooh, that's not good. Yeah, I literally have the exact same notebook. It's running fine on SageMaker. Yeah. Is anyone else having an issue? That's very strange. Austin, cannot import name validate links. Okay, well, oh yeah, good question. Let me see. Kernel, change kernel. I'm on Amazon. Let's see if this works. This is the one that I'm running it on my other notebook. Okay, there we go. So I guess if you change it to Conda, Amazon EI TensorFlow P36 or Python 3.6, that seems to fix it. So if you just kind of use the TensorFlow P36 backend, it doesn't seem to work. Okay, there we go. Cool. Appreciate it. Okay. That's literally the only difference between this notebook and the other one I'm looking at. Okay, so let's go ahead and run some of this stuff. This is going to be fairly fast. We've got Austin smiling on us. Okay, stepping back, we actually do have some interesting textures here. We've got some checkers in his shirt. We've obviously got the complexity of his face. We've also got some of these vertical lines in the background, whatever those represent. So let's go ahead and take a minute and define what we're doing. What we're going to be doing is some edge detection to start. And we're going to apply what's called a convolution. And a convolution is one of those vocabulary words that you absolutely need to know. So a convolution, and I'm stealing this from JC, is a function that interacts with another function and produces a third function. And so I'll talk about a more specific, I'll give you a more intuitive explanation in a minute when we talk about it. We're creating a function that is going to detect our horizontal edges, or we're going to detect our vertical edges. And so this is just a matrix. Oh, yep, exactly. So this is a matrix that represents a horizontal edge, and this is a matrix that represents a vertical edge. And we'll illustrate what that means in a minute. And so what we're going to do is we're going to apply the convolution from SciPy. And so SciPy and NumPy actually have some native image recognition and image processing functionality built in. I would recommend that you dive in. We're actually going to focus more on Keris tonight, but well worth diving in just to have an understanding of what's going on with SciPy. So we're basically going to apply that convolve function, and we're going to, as we can see, the edges themselves are they take on a shape of 400 by 400, which is the shape of our image. And take a look. When we resolve that object, what do we see? We effectively see what the image is represented when we have horizontal edges, right? Because you think about it, we have one type of nail, right? And sorry, that's the wrong analogy. We only have one way of looking at this, one dimension. And so if we scroll up, these vertical elements are kind of being lost, right? Now, if we repeat this, but let's say we're going to do vertical edge convolution. Let's rerun that. We get something that looks very, very similar, but what we're doing is we see the, the enrichment in the vertical dimensions, in that background, and we get to see, we don't actually see much in terms of those horizontal checkers on his shirt, right? So let's talk about, let's give you a more intuitive definition of what a convolution is. So a convolution is think of it as a transformation, right? And what you're gonna do is the way this is gonna work is we're going to have what's called a kernel. I want you to think of that as kind of like a moving window. And it's going to be a box, and you get to decide how big that box is. And what you're going to do is you're going to scan across this image in these little batches, whatever size kernel you decide, which we'll talk about in a minute. And what that's going to do is that's going to produce a feature map, right? And so what we're looking at here is our vertical edge feature map, right? But this is just resolved for us, right? And so one feature map is not going to give us the whole picture, right? And as a matter of fact, as you can imagine, we have multiple layers and we're going to do multiple convolutions. Looking at things in different dimensions gives us a more enriched model to represent these, our images, right? Okay, so that's the first thing you need. So you need to understand the concept of a convolution is going to scan and it's going to the image and produce a feature map. So feature map, I'm going to say it a couple more times because it might be on your quiz next time. Might be on your sprint challenge too. And so you can do a variety of modifications. We'll talk about some of those additional transformations in a minute, but effectively each layer is producing some kind of feature map, right? And so at the end of the day, you then pull it together and those feature maps contribute to a particular prediction. Okay, you can apply this in 3D as well. You can imagine scanning, this is a little bit vague, or a little bit meta, but in the same way you would scan across, the two-dimensional image, you can also scan in 3 dimensions, understandably. Okay, and if you have color, there are a couple of different ways to do it, but you would probably have one kernel that is specifically sensitive to red, right? And then you would also have something that responded to blue in the same way that we had separate, you can think of these as like filters for different textures, for different colors, for different signals that you might want to include or that you might want to detect. Okay, so as we'll see when we get into the Keris example, as you are taking these convolutions, you're taking this kind of two-dimensional map of pixels, and you're actually increasing the complexity of it because you are summarizing the data according to these different features that you're looking at. I mean, that's one way to think about it, is like you can say these are the horizontal features or the vertical features, right? And so you're actually kind of doing a type of feature extraction when you apply a convolution. However, there can be problems with that. And basically that's how convolutional neural networks get really, really big, right? And so there are a couple of things there are steps that are important to include, including like downsampling, or there's something that we're going to talk about in a minute called pooling. And pooling is another one of those keywords that I'm going to say again and again so that I'm sure you guys remember it. Pooling is where you are, if you've got like a 3x3 box, right? And those are the 3 pixels you're looking at. It's going to take the maximum value out of those 3, or out of those 9, I should say. So if it's 3 by 3, you have 9 pixels, and it's pulling the maximum one out. And so what you're doing is you're reducing the complexity of the data set. You're losing some information, but it's a way of think of pooling as a way of kind of summarizing the data so that you still have some information going through, but you do lose a little bit of resolution, so to speak. Okay. So let's go ahead and see what this looks like when we execute it as a model. So we're actually, as I said, these are going to be toy data sets, and we're going to pull these right from the Keras built-in examples. And so we're going to pull the sequential model. We're actually not going to use the model. We'll talk about that next week. We're going to pull dense layer. We're going to pull a convolutional layer, a pooling layer, and then a flattening layer. Okay, so we're basically pulling out the data set. It's just load data. So we're going to have some training labels, training images, testing labels. As we discussed a couple of weeks ago, it can be important to normalize your data. And what we're doing here is we're normalizing it to 255. And I believe it's 255 values of gray. I'm not trying to make a 50 Shades of Grey joke, I swear. But basically what you're doing is you're just normalizing it, right? It's good practice for neural networks. Okay, let's go ahead and run this, make sure there's no more errors that are popping out. Okay, so let's go ahead and take a look at some of the examples that we're going to be working with. And so we've basically got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 types of classes that we can try to predict. And here's some representations of them. So we've got a frog, we've got a truck, another truck, there's a deer, automobile of some kind, just an automobile, bird, horse, ship, cat, deer, horse, bird. Actually, this neural network is going to be better than I am because I can't even tell. It doesn't look like a horse to me, but anyway, that's why we spend all the time playing with this stuff. Okay, so if we're looking at one of these images, it is 32 by 32 pixels. And okay, let's go ahead and dive into the architecture. Okay, so we're going to instantiate our model. We have a sequential model that we're adding. And the first thing we're going to do is add a convolutional layer. This is 2D. We're only looking at, you know, it's just a 2D image. Hopefully that's intuitive to you guys at this point. The 3 by 3, this is where we define the size of our window, okay? So the size of our window is the size of our kernel. And think of this is, I'm sure there's going to be questions about like why 3 by 3. The fact is this is just another hyperparameter. And so if you increase the size, it may improve your model. If you decrease the size, it may improve your model, or the other way around. And so it really is dependent on the problem. Because there's so many examples out there, if you just do a bit of research and digging, you can probably find someone who has published a paper or has published a blog article about a particular data set and what window size works best. We're going to have an activation function like before, because so one of the cool things about the convolution is that we're doing feature extraction on it, but we're actually able to use that data that comes out the other side to update our weights. And so we need an activation function to, appropriately activate our values. The input shape is just going to be 32 by 32 by 3 because that's the dimension of our individual image. And then we're going to do a pooling max pooling 2D just refers to the fact that we're pooling the maximum value, and it's 2D, right? Pretty self-explanatory. We're gonna layer on we're gonna put a couple more convolutional layers on there. We're gonna pool each time. And then the next important thing here is our flattening layer. The reason being, remember we were talking about that increasing complexity? As you filter through these different layers, you kind of get this hierarchical output of feature maps. And in order to get it to play nice, you have to flatten it. And so we're just adding a traditional dense layer with 64 nodes. And then we have 10 classes that we are outputting. So in our output layer, we're going to have 10 nodes, and we're going to use softmax because it's a multi-class problem. And let's go ahead and print out see if it's actually going to run. Here we go. Okay. Okay, ignoring the future warnings, usually turn those off. Before we go on break, what I did want to highlight here is in our first layer, we've got 30 by 30 by 32. So remember, our images are 32 by 32. Why do you think we have the output shape of our first layer being 30 by 30? And you can either unmute or you're welcome to type your guess in the chat in Slack, because I can see both. It's 10 times the third value in our input. Not quite. So here's why. We have fair guess though. Okay, I see someone else typing something. See if anyone else has any other ideas.
Is it the 3 by 3 thing? Because
say more about that.
I don't know so we have 30. We have a 32 by 32 pixel image. If you put 3 by 3s to cover the entire pixel, and then maybe if you add the bias,
you can only fit 30 in there.
Yeah.
You can only, yeah. If you think about it, so basically we have a sliding window, guys, right? And so end to end, you can only fit 30 of those boxes in a 32 by 32, in a 32 by 32 image. So that's why we've got the 30 by 30. Okay, so the thing that I want to highlight here is our pooling. So thank you, Martin. Perfect. So the pooling layer actually doesn't have any parameters because that is actually just condensing the information, right? It's not increasing the complexity of our problem, but it is passing information into the next layer. So convolutional 2D, our second run of it, is still increasing, but it's because it's acting on a lower form of the data, it's actually reducing that dimensionality even further. So anyway, just keep in mind that's why these numbers, the shape of these outputs are changing. At the end of the day, when we flatten it, we're just going to flatten it into a 1024 length array. Plug it back into a dense layer, another dense layer. You guys are pretty familiar with this. Last step in any of these models, so we basically just built our model. The next thing we need to do is we need to compile it. You guys have seen this stuff before. We are pulling accuracy. We're using Atom as our optimizer. We're using sparse categorical entropy as a just by virtue of the nature of the problem, it's the one that applies. I don't particularly want to get into it. Let's go ahead and run it. And then this is the one that is actually going to take almost exactly the length of our break to, so Annika, no, 124 is actually not an arbitrary number. The flatten, no, so we're not telling it how to flatten it. In other words, see, we didn't actually pass in flatten. Like we didn't give it any kind of parameter or hyperparameter or argument that said flatten needs to be a particular size. So that is the shape that it's being reduced to based on what we're passing in. So it's a function of the dimensionality of the data that was passed into it. And maybe I didn't understand your question.
No,
okay,
I got it.
Oh, perfect. Okay, awesome. Okay, guys, so this is going to take a little bit to run. What I want to do is I want to take our break here. It's almost 8 o'clock on the dot. Get up, move around. And Ashwin, I see your question. Let's go ahead and take our break, and then I'll address your question when we get back. Okay. Have a good break. Yep, 5 minutes. I'll go ahead and set the timer. 5-minute timer. Okay, see you in a few minutes, and then Martin, there you are. Martin, to answer your question, yes, we are doing RGB. We're not, the Austin one was the only one we were doing. We were doing black and white. We specifically pulled that data out and made it grayscale. This is actually a colorful set, so yeah. Actually, sorry, not sorry. Maybe you guys heard that and we'll come back on time. Okay, let's go ahead and dive back in. Okay, so just to recap, Ashwin, so Martin answered your question. Ashwin, if it's not clear, let me know and we'll dive in. And Martin, yes, we are working on RGB stuff again. Okay, cool. Okay, so took a little bit. So with 10 epochs, we went from 53% accuracy to 70 or 69% accuracy, which is not bad. But actually we could, validation accuracy and, sorry, the test accuracy would be 70, or sorry, the training accuracy is 76, validation accuracy is 69. So not bad. Yeah, I wonder, I might run this overnight and see what we can get with 100 epochs, but not bad. Okay, so when we're actually evaluating the model as part, looking at our test set, so what I did here was my tennor's still going, our validation set, so I plugged in the validation data. If we're going to evaluate it like one final time as a true test, true assessment of our accuracy, our final accuracy is going to be, because we're using our test as we fed in the test data as our validation data, so we could see how it was updated in real time. But the final evaluation, just to kind of close the loop on that, was basically 69%. Not awful, but not fantastic. Yeah. Okay, so that wraps up the first piece of this. So what I want to just highlight is that there are a couple of terms you guys need to know. You need to understand, basically need to be able to define convolution. You need to be able to define what, in your own words, summarize how a convolutional neural network works. And then understandably, like the last 2 sprint challenges, you'll be expected to build one of these from Keris. But again, this is a toy data set. In practice, these take a lot longer generally. Okay. Okay.
Actually, I have a quick question before we move on.
What's up? Go ahead.
How do you determine how many layers you wanted to add there? Is that where we start with sort of a baseline and improve like we would with any other machine learning model?
That's another, so 2 things. So yes, it's a hyperparameter. It's harder to test it, with a formal structure because you have to kind of loop through it. But you can also do research, and because these are so such well-established problems, people have blogged the heck out of these. So you could actually just kind of look at what other people have done and try to learn from that. Okay, any other questions while we actually do, I can almost guarantee we're not going to go over tonight. So if you guys have questions, I'm happy to chat about it. Until Martin asks a question, then we're definitely going to go over. Okay, okay, let's go ahead. Okay, so this is actually my favorite part. It's not nearly as exciting as building your own image recognition model, but it's actually way more practical. So there's this concept called transfer learning, and I just thought this was the most amazing thing when I was learning about neural networks. Basically, what transfer learning does is it allows you to let someone else do the time-consuming, expensive piece that trains the model. You just take those weights and the trained layers and apply it to your prediction. So basically, it's a pre-trained model that you can then apply to your own problems, right? And in practice, this is how object detection. This is how convolutional neural networks are just applied across the board. And so one example, one particular place that you can look at some libraries available for, let's see, I think TensorFlow Hub is a library that includes reusable machine learning models. Let me see, where is the guide? And so it's got, so actually, Gwen, I'm not familiar with OpenAI. I'd have to look at it. But there's tons of Elon's platform. Yeah, sounds like something Elon Musk would get into. Anyway, I would definitely encourage you guys to dive into the documentation of TensorFlow Hub, because it's got all kinds of, it'll have examples for text classification. It'll have examples for image classification, for image detection. And because this is experimental, it's constantly being updated, which means that they're constantly adding stuff. Okay, here we go. I think it's, okay, so some examples, doing text classification, generating images, action recognition. That one's really interesting. Yeah, so anyway, there's some really cool stuff in here. So let's say that you work for a company that is going to invest in training a complex convolutional neural network. They invest millions of dollars in getting that coded data set. You train the model, it takes weeks, I tell you. What they're going to do is they're going to save that so they don't have to redo it every single time, right? It's pretty trivial for us to run a small random forest. It is not trivial to rerun one of these. And when you're starting to talk about thousands of GPU hours, and these are not tiny GPUs, these are very big GPUs. Reusing this stuff is huge. So, this is another sort of like toy data or a toy example, but, I just want to highlight that in practice, especially as a junior data scientist, you're more likely to apply this transfer learning, as we're talking about here, than build your own neural network from the bottom up. So not as sexy, but not as bloggable, that's for sure. But this is how you will actually use the data, use this stuff. Okay, so as before, we're gonna pull an example right out of Keris. But before we do that, I actually want to talk about ResNet 50 in particular. Net 50. So this is a really famous neural network, pre-trained neural network. Let's see if I can find the documentation. So examples. It's got tons of different, come on, where is it? Tons of different classifications trained into it. I can't seem to find it. Well, anyway, I'll post the documentation after class. But it's, I wouldn't say that it's overused. So when I tell you guys to work on projects like for your portfolio, I say avoid things like Titanic. Titanic's been overdone. Like any data science, you guys were dealing with Titanic in the pre-course, as I recall, right? Titanic does not convey to someone that you are a sophisticated data scientist. ResNet is not that type of thing. It's a high-level data set, and I would actually encourage you to include something like this in your portfolio, or write an article about it for Medium, because it actually carries a lot of weight in the field. Okay, so that said, let's do something with it, right? Okay, so we're going to import NumPy. We're going to import the ResNet 50 application from Keris directly. We're going to import image preprocessing tools from Keris directly, and then just some required preprocessing functions to, basically work with the data. Okay, so we're going to define a couple of helper functions just to make this a little bit easier. And at the end of the day, what we're going to do is we're going to use the ResNet as a tool, and we're going to wrap a function around it that's going to tell us whether, with a certain amount of probability or confidence, that the image contains a banana or not. I know, it's, yeah, we're curing cancer here. Okay, so in our image path, what we're doing is we're basically just loading the image itself. We're going to convert the image to an array. We're going to flatten it to an array, or expand it to an array, I should say, in the same way that up here we converted, we basically took this image of Austin and we converted it to a matrix. That's what we're doing here. Where did it go? Walking down. We're going to pre-process the input. Again, this is built into the workflow from ResNet 50 in particular. We're going to, and effectively what we're doing is this is all boilerplate. This is stuff that you need to do just to deal with the ResNet functionality. Then we're actually going to instantiate the model itself. Now remember, this thing comes with the weights pre-trained. So we're going right to the predictions step. We're not doing any retraining. We're going to, so our features are basically the predictions. In the results, we're going to decode that. And then we're going to print out our results. And then this is our banana detector right here. If it says it's a banana, we're going to return the probability that it's a banana. Otherwise, we're going to return a 0. Okay. So this is basically our banana helper function, but let's dive in a little bit more. Let's take a look at what we're actually, let's see what ResNet is printing out and giving us to work with, so that this piece will make a little bit more sense. Okay, so we've got 2 examples. We've got 2 examples. Oops, no, don't delete. I got myself a new keyboard for, let's see, is that gonna work? Yeah, okay, we've got a race car, right? Oh, good Lord, guys, please don't, oh my God. You're giving me flashbacks to like 1997 with the dancing banana. Okay, so you've got 2 examples. We've got a race car, right? And then in your repo, you've actually got a file called example0 JPEG, which is in fact not a banana. That is our, these are our, we're basically looking at a race car, not a banana, right? And so when we pass in image contains banana, it's going to print out a couple of things. So it's going to print out the results, right? So what this is doing is it's printing out the actual predictions, right, that ResNet is processing. And then it's going to tell us whether or not it thinks it's a banana. Okay, so when we plug in this example image, we get 90% confidence that it's a race car. We have like it looks like it's a 0.085% chance that it's a sports car, and a less than 2% chance that it's a tow truck. But these are different, these are things that are built into ResNet that it knows to identify. So it's basically just printing out the results of the, that ResNet is giving it. But it's giving us a 0, 0 because it's not a banana, right? So it's not predicting it's a banana. Let's see if we actually plug in a banana, right? So we have an image, example 1, that is in fact a banana. Does the image contain a banana? When we run this, we have the top candidates for objects pop up, and it's giving us a 6% chance that it's a banana. It's giving us a 6% chance that it's a hook. And it's giving us a almost 6% chance that it's a hatchet. So, you know, this thing is not fantastic, but it told us this was a banana. It was more certain about this being a banana than anything else. Okay, so like I said, I guaranteed you we would not go over tonight, so I'm happy to stick around for a little bit longer and chat about things, or you can take a dive into the assignment for tonight. What we've done from beginning to end was talk about what are convolutional neural networks, how are they applied. We've defined some key terms like convolution and pooling. If you stick around, I'll go on more of a biology rant to talk about how these line up with the actual by the eyeball. We've also talked about how to build one from end to end. So hint, hint, guys. This is the code that you're going to want to pay attention to. This should go in your cookbook. We talked about how dimensionality plays a role in training these things, how pooling can reduce that. And we walked through an applied concept, transfer learning, and how in practice you can save yourself the expense of training these models if there's something that already exists that can solve your problem. And we successfully identified a banana. So there's that. Okay, guys, so that's all I have tonight for you. I will happily stick around for the next bit, but I would love for you guys to dive into the assignment notebook. Let me see if I uploaded it. So I actually didn't upload it. Let me go ahead and load it. Let's go ahead and take a second, pause, take a break. Leave your questions or your favorite banana memes. Leave your favorite banana memes in the channel. That works too. But let's go ahead and take a minute. What questions do you guys have on this stuff? I see you leaning in, Gwen.
I'm trying to make sure I don't just accidentally ask the same question again, because I'm still kind of curious.
Okay.
If maybe there's a more Pythonic way to determine how many layers you should use, as opposed to sort of hoping on domain knowledge. Because I imagine when I first get to a job, I'm just not going to have it unless it's something that I already happen to know a lot about, which is basically like video games and cartoons. So that's not super useful to most businesses.
Well, okay, fair enough. So I would still reiterate that learnings from similar, even if they're not the exact same problem, can still help out. Otherwise, you're kind of looking at kind of classic hyperparameter tuning, which can be a really manual process. You know, and because training these takes so long generally, it can really be a difficult task to try to iterate through different numbers of layers or different types of layers or different activation functions, different things we've talked about as potential hyperparameters. It can be really tough. There are ways to, I think I'm going to stick with that. So if you were going to do that, I would basically create a for loop that creates a different number of layers and prints out your accuracy each time. That's just the simplest.
Would it not be like totally crazy to just do it on like a small subset while you're trying to feel this out if there's just not a lot of other research done?
Oh, no,
yeah,
absolutely. Yeah, absolutely. And actually the downsample, I think it's downsample is the pandas term, or resample, I can't remember.
It is.
You can take a proportion. And so, yeah, taking 10% is a good way to do it. But remember what your unit is, right? If a lot of the complexity doesn't necessarily come from the number of images, but it can be the size of the images as well. And so another thing you can do is you might do some batch processing to like resize the images themselves so they're smaller. You know, if you can still read it, again, you have to sort of like, that might be a good way to sort of like just play with it. Also consider different, and I actually have not experimented with this on my own, but you do also want to consider the file type. Some, like a TIFF, takes up a huge amount of like memory, and so processing that's going to be way more obnoxious than doing something like a PNG file or a JPEG file. So that is also something you could do to kind of like make your life easier, I bet.
I just have a simple question.
What's up?
I kind of had a little trouble focusing this lecture. Was the last case of the banana,
Yeah.
you said at the very end we were successful at identifying it, but it was...
Yes. Well, because what we're doing here is we're basically saying, so this gives us 3 pieces of information. This is printing out the results, and then it's printing out if it makes a prediction of the banana at all, right? It will return the probability of that banana, or it'll return 0, right? So basically, if ResNet is saying it's a banana in, you know, the top, if it's predicting it to be a banana at all with any kind of probability, it'll print it out, right? So yes, we're making a prediction that it is in fact a banana. I'm not saying obviously there's not a high probability, but it's the highest of all the different things it thinks it might be. So it said it could be a hook, it said it could be a hatchet, or it said it could be a banana. And so of those 3 things, the probability of it being a banana was the highest.
I see. But yeah. And in order to improve that, you would just train it with more examples of bananas?
I would actually do the opposite. I'd give it more things that look like bananas that are not bananas. So things like, I would give it more hooks, I would give it more hatchets, I would give it more counter examples so it can better discriminate it.
So both.
Yeah, exactly. But the point of this example is transfer learning, which is that you're taking something that someone has already developed and applying it to your own problem, right? And so the whole point of this is that we didn't train this. We're not modifying it. It's ResNet. It's something that's already been developed, right? And so in theory, yes, you would retrain it with more data, because you can always throw more data at neural networks. However, in this particular case, you don't want to retrain it because it would be a very costly endeavor. Does that make sense?
Sure. I mean, this banana case, I mean, kind of reminds of, you know, the various, you know, prove to me that you're a human websites. And it's kind of interesting. Sometimes they ask for the same image, keeps showing up. I mean, I see, you know, crosswalks or red lights.
You know what they're doing in that, right? They're training their own, actually, it's really clever. Google uses those CAPTCHAs, is what they're called, to train their own models, actually, for image recognition.
So they're not human detectors?
Well, they are. That's their goal. And I don't actually know how they resolve with bots, but when they, for instance, like for a while, so yeah, crosswalks or red lights or green lights or cars or storefronts, what they're doing is you're actually participating in their training, in applying labels to different images, which when I figured it out, I was like, oh, you clever jerks. Like, it's a really great application of it, actually. So actually, Dakota, do you want to share your screen and talk a little bit about your GPU versus CPU example?
If I could just quickly clarify
Oh,
something.
sure. What's up?
You said that if we use, say, for our Build Week project, we use ResNet 50, that's still worth writing a blog post about, even though it's been done a million times?
No, I'm saying it's worth featuring it in your portfolio. Right. No. Transfer learning on its own is incredibly boring. Unfortunately, you know what I mean? Like, but,
Yeah.
but it's very applied. And so my point is, if you do something with it, put it in your GitHub portfolio, because it's one of those things where, like, because there's so many blog articles about writing like a net new image recognition, you know, character recognition, whatever blog article, it will actually be worth it because it says that you can do something practical with it, which is buy a tool someone else has built and use that. Okay.
All right, so I actually went through and cleaned up the notebook and upgraded TensorFlow, and I broke it. So I put a little note under the notebook I shared. It works with any TensorFlow version under 1.8 with GPU compatibility, but it does not work with 2. So I had to upgrade to 2 for tonight's lecture to run locally. But yeah, it's there. Play with it. I seen, like I'd said before, almost a 4 times speed up between running CPU to GPU. So if you have the ability, it's definitely worth it. Just watch your versions.
Yeah, absolutely. Cool. Okay, so I'll hang on the line, certainly until 9. I don't want you guys to feel like you have to. I know that you guys love to lurk though, so you're welcome. If any questions come up, feel free to just shout them out and we'll review it. But I would encourage you guys to spend this time working on your assignment. And Tina, you can probably turn off the recording at this point.